All right, guys. This is going to be called the Momentum 2D Part 1 video. And I'm going to talk a little bit conceptually about the conservation of momentum in 2 dimensions. And I'm just going to do 4 examples. Okay? Now, we say that in the absence of an external impulse. Okay? Well, let's go back to the impulse momentum equation, right? Well, actually, I'm going to call this P prime. That's later. This is the initial momentum. This is the impulse. And this is the final momentum of the whole system. It could be a bunch of things. Now, in the absence of an external impulse, momentum is conserved. Okay, so we can say that P initial equals P final. But that's as a vector. In the past, the way we've done it is we've done it in one direction, in one dimension. Now, this can apply to 2 dimensions or 3 dimensions, which means that the total momentum in the x direction, okay, has to equal the total momentum final in the x direction. And the same thing for the total initial momentum in the y direction is equal to the total final momentum in the y direction. So that's the basis of the examples that I'm going to do next. Okay, so now let's do an example here. Let's start with the first example. So in the first example, I have, and I'm going to start with the simple stuff. I have a 2 kilogram object moving at 3 meters per second, and another object, 5 kilograms, moving at 2 meters per second. Now, I'm going to write the amount of momentum they have in red. So this has 6 kilograms meters per second. This has 10. Let's say they're going to intersect right there. They're going to collide. Okay. The initial momentum of the whole system is basically going to be, since they're going at an angle here, I can just probably just do, they're going at 90 degrees, I mean. I'm just going to do Pythagorean theorem, basically, right? So this one is 6, this one is 10, and this is the combination. That's the resultant, in other words. So if you figure this out, that's your initial momentum, and we should get 11.66 kilograms meters per second. Now let's say these 2 objects stick together, right? So they become one. This initial momentum should equal the final momentum. Okay. So now this is also going to be the final momentum, okay, because they stuck together. All right, so now how do I figure this out? Well, this is just 11.66 kilograms meters per second, and I can figure out this angle here. Well, that angle is just the inverse tangent of 10 over 6, which is equal to about 31 degrees. Okay? Now, how do I find the velocity? Well, the velocity after the collision is just going to be the momentum after the collision, total momentum after the collision. Now they became 1, divided by the total mass, which is 2 and 5, which is 7. So, and if you do the math here, you should get a velocity of 1.67 meters per second. Now, keep in mind that P is equal to mv as vectors. Since the mass is positive, P and V will have the same direction. So here, as our final answer, we're going to write, okay, the P prime is equal, as a vector, is 11.66 kilograms meters per second at 31 degrees. I guess we can look at north and east. So we can look at right as east and up as north. North of east. Now for the velocity after, that's going to be 1.67 meters per second at the same angle, always. All right. The next example. Okay, let me just erase this. Okay. The next example, we're going to have 2 objects not coming at 90-degree angles. So one object has got a mass of 4 kilograms here. It's coming at 5 meters per second. Another object, 2 kilograms, is going in this direction at 3 meters per second at an angle of 30 degrees. And this angle here is 40 degrees. All right, so I'm going to write the momentum of each in red. So this has 20 kilograms meters per second. This has 6. And they're going to collide. So the moment they're going to collide, they're going at these speeds. Okay? So let's just, and they're going to stick together. So I'm going to try to draw the 20 kilogram meters per second here. And then I'm going to come to the head of this one, and I'm going to do the tail of this one. And by the way, you can start with this one and go here and do the other one. It doesn't matter. Remember, we say that the addition of vectors is commutative, meaning like you can change the order. And this is a 6. So this is the resultant vector. So basically what we're trying to find, we're going to try to find this P prime, okay? And we have to figure out what that angle is. That's the goal. Now, I can do these 2 ways. I can do this using, I'm going to do a chart method, and then I'll show you, you could do this much quicker with the law of cosines. So let me do the chart method first. So the way I'm going to do this is that I'm going to break this down into components of momenta for each. Now here's the 4 kilogram mass. This is the 2. This is the sum of the 2 after they stick together. And that should help me figure out the total momentum after. In other words, the sum of the momenta before the collision has to equal the sum after the collision. So this sum represents the before and the after. Okay, so I did the math here. You can see that the x component of this 20 is positive. The y component is negative. You see this, for the 2 kilogram, you're going to see that the both positive. The components of the 6 kilograms meters per second are both positive because it's right and up. While I did the math, you can do SOHCAHTOA to figure out these numbers. Okay, and I'm going to try to make the angles. I'm going to try to do 30 and 60 and 45 as much as I can. Now, if I add 20.52, because, and the reason I'm adding because I want to find total momentum. Is the total momentum that's conserved, not the momentum of each. Okay, negative 9.86. Now the picture that I drew kind of looks like it makes sense. Now, all I have to do now is I'm going to save this for to do a law of cosines. All you have to do now is you're going to see that your vector goes right and down. So it should look like that. So 20.52 right and 9.86 down. And you have to figure out what this P prime is, which is the same thing as PO. Okay? Now if you do if you do a little bit of trig, you should get 22 P prime equals 22.76 kilograms meters per second at, and you should get an angle about 14 degrees. That's south of east. Now the V prime should be equal to 22.76, but you have to divide it by 6 because the two masses are stuck together. So you should get 3.79 meters per second at the same angle. So that's one approach. It's long, but it's safe. Now let's see if we can do this with law of cosines. Let's see what law of cosines holds. So I draw my picture here now. I make a triangle, and by the way, this is only possible if the vectors that you have from before the collision and after the collision add up to 3 vectors. In other words, if I had these two colliding, and when they collided, they separated, I have 2 before the collision and 2 after to deal with. I can't make a triangle out of that, so I can't do law of cosines. So here. Now, this angle here is 40 degrees. Okay, this angle here is 30 degrees. So I think I can figure this angle as being 110. And then once I do that, this is 20, this is 6, right? Maybe I'll write this in red. This is 6 kilograms meters per second, and that's 20. Now, if you do law of cosines, you should see that p prime square, well, I'll take the square root, is going to be 20 squared plus 6 squared minus 2 times 20 times 6 cosine of 110. And it's much, much, much quicker. And that's 22.76 kilograms meters per second. Now, the velocity you can just divide by 6, like I said earlier. The angle for the velocity will be the same as the angle for the final momentum. Now, let's see how we can figure out the angle. I need to figure out their angle. But before I can get to that angle, I think I can find out what this angle in blue is. I'll call it theta. And I know between that question mark and theta, that's 40 degrees altogether. So if I can figure out that angle in blue, then I can just subtract from 40, and then I'm good. All right, so I'm going to do law of sines. Sine of theta over 6 equals sine of 110 over whatever I found. Okay, and you should get an angle equal to let me see. $14 degrees. Actually, previously I copied the wrong angle. The angle should be 26 from what I just said earlier. If you do the trig, you're probably going to find that I made a mistake. Okay? Okay, so this angle here is 14. Okay? Now the whole thing is 40, so you're left with 26 here. Okay, so the angle is 26 degrees south of east. Law of cosines is quick. Now you always want to check that you don't have that, what do you call the ambiguous case in trig. So 14 has a 6 across from it. 110 has about 23. Okay, so what's left? That's 20, so that's about 54 degrees. Has the 20. So I think, is that 54 degrees? 24. Hold on a second. Is this? Let me just do the math here because these numbers might be wrong. Okay, so I'm going to do sine of 110 divided by 22.76 times 6 second sine. Okay, so this angle here is 14. It's got a 6 across from it. Yeah. And then this angle, let me see, 110 plus 14 minus 180. This angle here is 56. 56. Okay, so I think it looks fine. So you have 110, it has a 23 across from it, you have 56. So yeah, so the triangle is fine. Okay, I thought I made a mistake, but yeah, the triangle is fine. So that's 26 degrees. So that's law of cosines. All right, one more example, 2 more examples. So here is 3. For the third one, we have an object that has a mass of 10 kilograms moving at 5 meters per second. This angle here is 30 degrees. Okay, and it's going to break into 2 pieces. So one piece is 4 kilograms, and it's going to be going at 60 degrees, not drawn to scale, at a speed of 7 meters per second. We want to know what happened to the rest, which is 6 kilograms. That comes from 10 minus 4. So here is the chart method. Okay, so initially you only started with the 10. Is the x, here's the y component. So you do the sum. That sum has to be the same as the sum of the momenta in both directions when they separate. Now, you have a 4 here. You have a 6 here. And the sum has to be the same in both of these places here. All right, well, I did the math. So for the 10, it's positive and positive. So you do trig. You can separate this, in other words, into components. you do the same thing here. 43.30, 25, the sum is 25 and 43.30. Okay. For number 4, after the explosion is plus and plus, that's 14, 24.25. Okay, and this is 43.30 positive, because it's the same as the sum here, conservation of momentum. Okay, now what do I need to 14 to get 43.30? I need 23.3. Here I need 0.75 positive. Okay, now I know that my 6 will be going in this direction because the x is positive and the y is positive. This is 29.30, and this is all momentum, not velocity. This is 0.75, and you can find p after the explosion for number 6 by doing Pythagorean theorem, and you can figure out this angle. And the answer is 29.31 kilograms meters per second, and the angle is 1.5 degrees north of east. Okay, now let's see how we can do this with trig, law of cosines, in other words. Okay. Okay. So initially I had this here is 50. Okay. This is the number 10. The other one is 28. Okay, that's 28. Okay, now after the collide, after the explode, I have to have 50. So my initial momentum vector has to be equal to my final momentum vector in direction and in magnitude. So now I have to just complete this triangle, right, to figure out the momentum of 6 after the explosion. Okay, so let's try that. Okay, so I did it with the chart. Now I got to do it law of cosines. So now if I look inside here, this whole angle here, that's 60. This angle here is 30. So I'm left with 30 here. All right, I hope you can see that. 60 all the way down to there. That's 30 because of here. So I'm left with 30 in there. So I think if I do law of cosines, I can do P6 prime equals radical, okay, of 28 square plus 50 square minus 2, 28, 50 cosine of 30. And we should get 29.31, just like we found earlier. It's much quicker. Okay. Now to figure out the angle, I need to find this angle here, basically. But I think before I can find that angle, how about if I find this whole angle? Okay? If I find that whole angle, I know this angle here between the dotted line and the 28 kilogram meters per second vector is going to be, this is going to be 60 degrees. Yeah, this is going to be 60 degrees. Okay, this is still 28 because of the alternate interior, alternate interior angles. So if that's 60, this here is 120. So if I can figure out the blue one, I subtract from 120 and I'm good to go. So let's figure out that blue angle here, theta, in blue. Okay, so I can say, well, sine of theta over 50 equals sine of 30 over P6 prime, which is 29.31. And if you do the math here, you will find an angle you're going to find two things. Let me try it. So sine of 30 divided by 29.31 times 50. Oops, didn't do it right. Sine of 30 divided by 29.31 times 50, and we do the sine inverse, and we get 58.53. So we get that this data is 58.53. Now, if you look at it, 58.53 is not good, because you're going to see that you're now respecting the triangle inequalities. You're going to see that 58.53, and that's what? So here you're going to end up with more than 90, okay, facing a smaller side than 58.53. Remember when we talked about this early in the year, it could be the angle or its supplement. The supplement of 58.53, I'll just go 58.5, is 121.5, because this one doesn't work. The triangle inequalities are not respected. So if you subtract 120 from there, you get your 1.5. All right, last example. Last example, I cannot do law of cosines. So for the last example, I have a 4 kilogram object going out at 6 meters per second. The angle is 30 degrees. Another object, 6 kilograms, at an angle of 45 degrees, moving at 10 meters per second. All right, so this has a momentum of 24. This has a momentum of 60, right? Now, when they collide, this is after they collide, the 4 is moving this way at 8 at an angle of 60 degrees. So which means it has a momentum of 32 kilograms meters per second. I want to figure out what happened to the 6. Now, this one I have to do with the chart. So here we go. And I'll do this quickly here. So here's the 4 before the collision. Here's the 6 before the collision. The sum before the collision. Okay. Now I'm going to do the 4 after the collision. Well, I don't know much about the 6 after the collision. And then here's the sum after the collision. Okay. Now, if I do a little bit of trick, I can see that this is plus and minus. Both of those are negative. Okay, so here are the numbers that I got. 2078, 12, 42, 43, 42, 43. The sum is negative 21.65, negative 54.43. For 4 after the collision, it's going to be a plus and a minus, 16, 27.71. Now, I don't know much about the 6, but I know the sum has to remain constant. So this is going to be negative 21.65, and this one has to be negative 54.43. All you have to do now is fill in this blank here, so that 16 plus something gives you negative 21.65, and this blank should be negative 37.65 and negative 26.72. Now you have the components of vector number 6. And they're both negative, which means it has to be going left and down. Well, it's got 2165. The component to the left is 2165. The component down is 54.43. Oh, I copied that one. I mean, 3765 and 2672. Now, if you do your Pythagorean theorem, you should get this momentum as 4617. You can find out that angle is, and that should be 53.36 degrees south of west. And if you want to find the velocity, you just take that number and divide it by 6, because the mass of the unknown is 6. And these 4 examples should be enough for you guys to understand the momentum or conservation momentum in 2 dimensions. All right, see you later. All right, I'm out. Peace.